Welcome to this explainer. Right now, we're going on a high-energy journey straight under the hood of your everyday devices. We are going to decode the secret language of computers. We'll start with the concrete reality of what you actually see on your screen, map it out visually, and then slowly build up to the abstract, invisible math that makes modern tech literally possible. Think about this for a second. How does your computer know exactly what shade of orange you want? When you're designing a presentation or just browsing a website, you see millions of distinct colors. But here's the thing, your computer doesn't know what orange or blue is. It only understands raw data. So how on earth does it translate that data into that exact, perfect sunset orange on your display? Okay, let's dive into this. Notice that specific 6-character code right at the bottom of the HTML color picker. FF9966. That right there is a hexadecimal code. And it isn't just random letters and numbers. It's a set of hyper-precise instructions dictating the exact intensity of red, green, and blue light your monitor emits. The FF tells the computer how much red to use, the 99 handles the green, and the 66 dictates the blue. Just by tweaking these hexadecimal values, you can produce over 16 million different colors. Absolutely wild, right? But hexadecimal codes aren't just for beautiful colors. They also show up when things go terribly, terribly wrong. We've all faced it, the dreaded blue screen or a random system error pop-up. These cryptic codes automatically generated by a computer, like 0x5 or 0x1f, are actually a map. While they might just look like complete gibberish to us, for a programmer, these hexadecimal numbers are pinpointing the exact memory locations where a system process totally failed. Section 1. Visualizing the switches. Denary versus binary. To truly decode these colors and memory errors, we really need to shift our focus away from the surface level of our screens and go way down into the silicon itself. Deep inside your device, there are no colors, there's no text. There are literally only millions and millions of microscopic switches. And this brilliantly illustrates the difference between how we think and how a computer thinks. Our human system, decimary or base 10, uses 10 digits, 0 through 9, and our columns are multiples of 10, units, tens, hundreds, thousands. But the computer system is binary or base 2, because those tiny switches I mentioned can only be in one of two physical positions, on or off. Binary only uses 2 digits, a 1 or a 0. And because it's base 2, the column headings double every single time, 1, 2, 4, 8, 16, 32, 64, and 128. Let's look at this spatially. To convert the 8-bit binary number 1001110 into a human denary number, it's actually a super straightforward pictorial process. Step 1. We just write our binary column headings from 128 down to 1. Step 2. We place our binary sequence directly underneath them. Step 3. We simply add up the column headings that have a 1 in them, which just means that specific switch is on. So we add 128 plus 8 plus 4 plus 2, and boom, that equals 142. Just by looking at which columns are active, we've basically decoded the machine's language. Section 2. The hexadecimal bridge, a shortcut for humans. But here is the massive problem. Imagine trying to write a really complex computer program, or trying to find a network error using only ones and zeros. Just a simple 16-bit number looks like a huge, confusing string of characters. Programmers would literally lose their minds trying to read, copy, and remember all of that. So we need a bridge between the machine's endless ones and zeros and human readability. That bridge, it's hexadecimal. Because it is a base 16 system, it needs 16 different digits. It uses the normal numbers, 0 to 9, and then it uses the letters A through F to represent the values 10 through 15. The real magic of hexadecimal is that it acts as this brilliant grouping shortcut. Because 16 is 2 to the power of 4, exactly 4 binary digits correspond perfectly to one single hexadecimal digit. So 4 microscopic switches neatly shrink down into one clean character. Let's move to it and see how this builds a much, much easier system for programmers. We start with a long 12-bit binary string, 10111110001. Step 1. Take the string. Step 2. Starting from the right side, we simply split it up into visual groups of 4 bits. Step 3. We convert each group using our table. 1011 becomes B, 1110 becomes E, and 0001 becomes 1. So that overwhelming string of ones and zeros seamlessly shrinks into 3 simple characters, BE1. This is exactly why error codes, MAC addresses, and HTML colors all use hex. It's an absolute game changer of a shortcut for humans.
Section 3. Abstract Math, Binary Addition and Overflow.
All right, now that we've mapped out how the switches are visualized and translated, it's time to step a bit deeper into the machine. We're going to look at the totally abstract realm of how a computer actually performs mathematics using literally nothing but ones and zeros. Adding in binary follows very similar rules to the decimal math we all learned back in school. You stack the numbers and add the columns right to left. 0 plus 0 is 0, 1 plus 0 is 1. But remember, the highest digit in binary is 1. So what happens when you add 1 plus 1? Well, you get 0 and you carry a 1 over to the next column. If you happen to add 3 ones together, the sum is 1 and you carry a 1. The computer basically ripples these carry values from right to left all the way across the microchip.
But there is a very real physical limit to this math, and that limit is 255. This number is incredibly important. If you have an 8-bit register, meaning you have exactly 8 microscopic switches, 255 is the absolute maximum denary value it can physically hold. That's the number you get when every single one of those 8 switches is flipped up to the on position. So the crucial point is, what exactly happens when a computer tries to add 2 numbers together and the answer is bigger than 255? Well, if the calculation generates a 9th bit, but the hardware only has 8 physical slots to put it in, that 9th bit simply vanishes and literally just falls off the edge of the register into the void. We call this an overflow error. It's exactly what causes famous glitches in retro video games, like that infamous Pac-Man kill screen, and it causes the computer to spit out a completely incorrect, much smaller mathematical result. Section 4. Logical binary shifts, math as physical movement.
Now, computers don't just calculate math by adding up columns. Sometimes they perform math by literally, physically moving the numbers across the board. This abstract concept is known as a logical binary shift. By shifting a sequence of binary digits just one place to the left, the computer instantly multiplies the value by 2. Shifting it one place to the right, that divides the value by 2. And as those bits slide over, the empty spaces left behind are just filled in with zeros. It is incredibly fast. But, you guessed it, just like with addition, there's a risk. If you shift the sequence too many times and accidentally push a 1 right off the edge of the register, that data is lost forever, which results in a pretty major mathematical error.
Section 5. The abstract negative, 2's complement.
Okay, so we've covered colors, errors, conversion, addition, and shifting, but there's one critical, highly abstract question left. If binary is literally just physical switches that are either on or off, how on earth does a computer understand numbers below 0? Like, how does it represent a negative number? The answer is a genius concept called 2's complement. Now, what's really interesting about this slide is the tiny, elegant little change it requires. The standard 8-bit headings we looked at earlier start with a positive 128 on the far left, but the 2's complement format, it starts with a negative 128. The computer solves the entire abstract problem of negative numbers simply by turning that leftmost bit, the most significant bit, into a negative value. If that specific switch is on, the computer instantly knows the entire number is negative.
Computer scientists came up with this brilliant 3-step mathematical trick to instantly convert a positive binary number into a negative one using this format. Let's say we want to write negative 67. Step 1, we write the positive version of 67 in binary. Step 2, we invert every single digit, swapping all the 1s for zeros and all the zeros for 1s. Step 3, we simply add 1 to that newly inverted number. The final result? Negative 67. It's honestly a breathtakingly elegant piece of abstract logic that allows simple on and off switches to handle completely complex negative accounting. So, we've journeyed from the concrete reality of a super colorful HTML web page, visualized the spatial columns of binary switches, and built all the way up to the abstract logic of binary addition, physical shifts, and negative complements. But I want to leave you with this one final mind-bending thought. Everything we looked at in this explainer today was entirely constrained to 8-bit registers, with a maximum limit of just 255. Your current phone, your laptop, they run on 64-bit registers. If an 8-bit machine is bound by a tiny 255 limit, just try to imagine the unimaginable scale, the blazing speed, and the sheer complexity of the abstract math racing through your devices every single second. Thanks so much for joining me on this explainer today, and honestly, I hope you never look at a screen the exact same way again.